Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Well, ladies and gentlemen, I should thank you for the invitation to come up here. It's a great pleasure, but it's also a little bit an honor because, you know, I will talk about this book, but I also like to just play around with it and talk about maybe different things. We have a limited audience, so please interact. Just, you know, ask a question or throw some objections if you feel like it. I was realizing, well, first of all, I mean, I must say, I got in touch with Microsoft Research in a somewhat surprising way, because I'm now down at Santa Barbara. And what is the surprise? I am all surrounded by people from Microsoft Research called the Q Project. And I must say, I'm highly impressed by what these people are doing and what they can do. So people like Alexei Kitayev and Mike Friedman and so forth. Very, very impressive and interesting stuff. So you were saying that you weren't understanding what I was working on in Santa Barbara. Let me tell you, I don't understand either, and that's why we have to work very hard on it. That's not unusual. Now, and also when coming up here, I was realizing actually something interesting. My book is a book, The Equations, Icons of Knowledge. Now, icons, that suggests already they are in some sense established. They have been repainted very often. And I am very fully aware of something, and that was already explained to Tamara to me. This lecture series, or this book series, is on peripheral things to your own science, which is, I presume, largely computer science or related software development and all the things that come with it. And in fact, the things I am describing is, in some sense, the old science. It's the old thing of decoding. Our problem is decoding. You have a puzzle, you know. Let's see whether this works. It does. Oh, it does strange things, though. How does that work? I don't know what this means. I haven't seen this button before. Well, yeah, that was the idea. What it was here, what does it say, you know? And so you have to art, you know, for clover, for bridge, and so forth. And if you ask for the first time and people look at it, they may have a hard time, and you have to give them a hint, like this, for example. And then maybe they recognize what it says, you know. It's just a bunch of numbers, and they are mirrored, and they just fit. And so I always think that a lot of the things we are confronted with have to do, if you don't see it, it's infinitely difficult to understand it. And once you see the clue, then complex things may be translated into very simple things. But you must know, better than I probably, that if somebody would throw the code of the Windows operating system to you, and you just get all the zeros and ones, and somebody says, well, figure out what's going on there, it may take a lifetime. Or maybe you will never get to that point. And so this is maybe the difference between, this is the boundary between you and me in some sense. I have spent a large part of my life in trying to decode things, getting the data, getting things, and trying to understand what's beneath it, what is under there. And you, as far as I can see, and I must say I'm highly impressed by what, you know, computer science and everything around it has achieved in the years that I am active in the scientific field. I mean, I started in the early 70s in Stanford, and it was, of course, a madhouse of new things and new ideas. And I realized now, when I was moving up here, that actually maybe you guys are coding. You are coding a new part of reality, where I was decoding, say, the reality we were all confronted with, and answering the questions that we all ask when we are young. And you might even wonder what the thing you are now coding, in some sense, will be decoded later, or will be a new puzzle to decode for generations to come. So here are other things. You see, it's always the same. This is a kind of, we all say that our children are getting spoiled because they're all addicted to these stupid games and these little screens, and they sit there. And of course, but there are also funny creative parts to it. This is, of course, a new language that you are all familiar with, I think. These things have meanings. For example, here there are a few, you see. So it's nice to see that all these inventions can be done. But also here, it takes for me ages to figure out what it means and to decode these things. So here's another part of it. And so there are all these different cultures of analyzing and thinking about things. Now this book I have written, as I said, is somewhat orthogonal to creating new code. But it's more the reflection, it's more getting back and being aware of something that we are maybe losing. Because the motivation for this book came out of the observation that in a society which becomes more and more consuming and leaves more and more of the functions to maybe machines, to maybe intelligent programs and stuff, somewhere there may be an alienating effect. You get disconnected from all kinds of base rules of the game or base concepts. And so that was my idea that, and I quote Einstein here, what I value in life is quality rather than quantity. Just as in nature, the overall principles represent a higher reality than does the single object. So in that sense, I try to undo the full width of the hard sciences of as much as possible. And of course, we have done thousands or millions of experiments, and these experiments, one by one, can be extremely interesting and extremely smart in the sense that they were designed to find certain things out and to get behind what are the principles that, which are referred to here, which are underneath the reality we live in. So if you do that, and so here is the task in some sense, and it is an amazing fact. You see, the most important task for scientists is to search for the most fundamental laws from which a picture of the world can be deduced. There is no logical path that leads to these elementary laws, only an intuitive one, based on creativity and experience. Well, that's fine. But what is striking is the following sentence. With such a methodological uncertainty, one would think that an arbitrary number of equally valid systems would be possible. However, history shows that of all conceivable constructions, always a single one did stand out as absolutely superior to all others. That is a fact, that is an experience fact of us physicists and people in the hard sciences, mathematicians, and so forth. And I would be interested to know whether you share that view, for example. Is it true that if you fully develop certain software tools which have certain a certain objective, that once that objective is clear and it has been developed out, then indeed there are such things as the way to solve the problem? That seems to be suggested by the things we see in nature, that there are certain optimal solutions to the problems posed by our physical environment. Anyway, of course, this talk will not be too high in the sciences. It's exactly my concern and my drive to write this book had to do very much with the fact that I feel that science is actually at the heart of culture. It is an integral part of culture. And what we see is that it gets separated more and more. And it's not only the sign that, for example, our youth will not maybe choose science or mathematics or these kind of difficult subjects, but it's also true in a much deeper sense that we think often of science as purely technology, as a product in terms of products, while we all know that science has a tremendous cultural dimension as well. It is very influential on how we think about, well, maybe our existence, our place in the cosmos, and the cosmos itself. It has reshaped our view on the universe and our place in the universe. And that is something that determines a lot of cultural values, as well as that it can be, generate a lot of modern ideas and technologies. So I thought it would be important to kind of communicate that all this science, in some sense, can be summarized in an optimal way, in the most compact way that knowledge can be condensed. And I chose to take those equations I have, of course, studied and learned a lot about. So that was the statement. Here is a somewhat provocative picture, which you are also all familiar with, because we talk about it a lot in politics. We say there is first this problem of illiteracy. Well, you solve that, and then you discover, hey, there is something called innumeracy. There's a lot of people who are certainly just afraid of numbers. You tell them, okay, how many diapers are there processed every day in the US? And they say, what? How can I know this? And everybody knows. You can just calculate. If you have any notion of quantities, then that's not a hard question to answer, approximately, I guess. And so in some sense, then there is this other level to talking about it, and it sounds a bit, I'm willing to reverse the arrows, it doesn't matter, but it's true that there is also, beyond the numerical and the numeracy, there is also this dimension which is in some sense more abstract, I would say. And that is the familiarity with the language of mathematics, which maps, of course, enormous parts of reality into a very abstract language. And what we found was, of course, that though mathematics was the most artificial of all languages, well, maybe you have more artificial languages, it was able to capture nature as no other language. So here is the drive of the book. And it's somewhere in there. I'm not going to read from this book, of course. We're just going to discuss it. There is a fashionable dogma about popularizing science which imposes a veto on the use of equations in any popular expose of science. Some people hate equations while others love them. The veto is like asking somebody to explain art without showing pictures. In this book, we override the veto and basically turn it around. For a change, the equations themselves will be at the focus of attention. And we talk about equations as icons of knowledge. We should certainly show them in all their beauty. So the idea was to just put these equations as icons and then describe in a very brief, very sober way what these equations mean. And thereby we give a kind of a summary of centuries of science and development of science. So mathematics as a language of nature. And then it's nice to note, a lot of people always say to me, okay, you are a theoretical physicist, but then you are a mathematician. And that's, of course, not true. I may be very skillful, or I may like mathematics. I can do it maybe quite well. But I am certainly not a mathematician. In the sense that for the sciences, the natural sciences, and that's what I'm talking about, mathematics is a language in which nature expresses itself. That means that the great equations of science, say of physics, like E is mc squared or whatever, there is that equal sign, and that equal sign is a statement which of course is a mathematical equal sign, but it is a statement about the state of affairs in nature. It makes a statement about how things work in nature in a very compact form. And so that is the important thing. So this book does not teach mathematics, and even not really physics. It just explains what these core symbols actually mean and why they are so important. So where mathematicians study and generate mathematics, because just asking the questions of consistency, of these kind of things, they generate every time new layers. And at the other hand, the natural sciences use it as a language, but also demand sometimes completely new ways of doing mathematics. As you may also know, that has happened in computer science as well. So this was the machine we all are probably in some sense familiar with. So wonder drives to looking at the world. We always ask the same questions. What is everything made of? What is the universe? What is time? What is space? what is life, what is consciousness, etc., etc. And we try to figure it out by looking at things and get certain knowledge about it. And of course, the thing is that once you have this knowledge, you produce often exponentially many new questions. Now, hopefully not exponentially, but certainly new questions are generated. So in spite of answering maybe a few, you generate at least as many, it seems. So yes, wonder is the seed of knowledge, as Francis Bacon said. Now, in these harder sciences, there is a special circumstance, because this is something that applies to everything. It applies to philosophy, it applies to everything. But there is this peculiar fact, which I summarize here. If we are curious and we look at the things, we may discover funny things. Like here, you look in this droplet of water, and you see that, hey, in the middle there, these lines of the leaf under there are magnified. And if you then also realize and have observed the fact, that glass has a similar property, then of course you are already halfway discovering the lens. And so this is important. Once we have a certain knowledge, it may allow us to manipulate the things we are understanding. And by that path, you could say, so there's a kind of a double helix idea there. We see that there is a feedback loop into observation. Because once I have invented the lens, then of course I can, it's like moving up in a completely objective sense. Objective sense, my sphere in which I can make observations and thereby acquire new knowledge. If I have a lens, I can look at the stars, discover moons, I can discover all kinds of weird things. I can make a microscope, I can see that there is life on a microscopic scale and that it is very different from the scale we are, and so forth and so forth. And we can invent the spectacles, which of course is a great invention and a great thing to do to mankind. So in that sense, everybody's observations have been broadened by this wonderful little invention. But once we have this picture, the story gets more interesting, because now, you see, I started there, and then I do this, and I draw this. But once you have this double helix here, it's like a machine. It's like a machine generating knowledge, because it doesn't really matter anymore who is first. It may be that now here somebody starts making things, and we really get back to very, very new fundamental questions. So there are these two things. I always say, okay, here is maybe the technological extreme. Here are the product improvers, and here are the philosophers, or something like that. And in between is this whole play of science and this language, this exchange. So I like that picture in that way, that it shows that this will never completely work. When I was in the early 70s in Stanford, I brought in people from Philips laboratories, you know, to go in the artificial intelligence lab, because I had some friends there, and they were doing all these crazy things there, you know. For example, no, that was actually in the other lab there down the street with Xerox, where they were inventing the mouse because they wanted to have small children play on the screen with a little point and a dot. That was the first moment. So my friends who worked at Philips labs were visiting me and said, okay, I'll bring you into this lab and you can show, so you can see what they're doing here. And so they went in, and they saw actually this little game. Barbara Colkin was doing that, and so playing that, and so they had all kinds of programs doing all kinds of neat things. The guy came out and told me, well, this is just a kindergarten. This is not interesting for us. We are producing machines, this and that can do this and that and that. And so the guy was just completely here, and the other part was there. I thought, yeah, the lessons I learned from that is that we have to keep an open eye. Anyway, this is my remark here, that at a certain point, and that is what I like about being here, and I would love to talk to you guys on all this question of, we always think of imagination being a kind of a poor repeat or an imitation of reality, but in the meantime, of course, it's the other way around almost. We can see that what we have imagined, namely in the early 70s, for example, with computers and working and worrying about hardware or about software also, especially at that moment already, very, very much so, you create new realities which expand and which come from imagination. So here is something that I always like to think. And this summarizes the book in an unusual way, and it's not even, this picture is not even in the book, so it doesn't matter. Here, man is still some kind of central, and he can look both ways. He can look to the larger scales and learn about things, you see. And discover maybe that the earth is not flat, and maybe discover, revolution after revolution, that the earth is not in the center of the cosmos, and so forth. So, we have worked on this program for a very long time with the greatest inventions to figure out what was going on. And we have gone a long way. We have seen that nature has organized itself on all these incredible scales. 10 to the 0, it's 1 meter, million meters, etc. So thousands of kilometers, etc., etc. And so we are up there. We have, you know, the Earth being just one planet, the sun being a star, one of the stars in 100 billion stars in the galaxy, and the galaxies cluster again, and you have superclusters, and so you get further and further away. And our Earth, our good old Earth, we have in some sense, we have been deported to a rather arbitrary outside spot somewhere in this universe. And at the other hand, we could, of course, go to the microcosmos. We could look to the inner worlds. And, of course, here we also discovered that the nature has organized itself in an extremely beautiful and interesting way, all the way down, nowadays, if you think of great accelerators, 10 to the minus 20 meters, which is, of course, very small. And then you see that, that the sciences are really all over the place. And it's interesting to see that everywhere, at any level where nature organizes itself, whether it's the nuclear or the atomic or the chemistry or the cosmology, everywhere where there is a definite structure, you get these new sciences discovering and describing these particular parts of reality. And then, of course, if you take a large distance and look really as large movements in the history of science, you see there is this drive to understand the universe at larger and larger scales, at larger and larger times. There is this drive to understand that universe on smaller and smaller scales, going to the ultimate limits of questions like, is there always a smaller substructure? Can it stop at a certain point? Is this Chinese boxes or Russian dolls, or what is going on? And at the other hand, we have come to realize and discover the importance and the vast terrain of what we now maybe call complexity, the science towards complexity. And so this is the picture, the overall picture. And of course the book is now centering about certain equations which I consider to be crucial. And in fact, not all of them. Of course, in the heart, I think, of really quantitative science, this was a big turning point. We have the laws of Newton and Maxwell. You see, there's 200 years in between. Newton was the first one to really discover new mathematics, and using that mathematics to make a very precise model which made lots and lots of predictions, and also explained all the knowledge that was available at that time about both the terrestrial mechanics, but also on the mechanics of the sky and the stars. So we'll say a little few. Of course, if you really think of great turning points, I think then the evolution theory was the first perspective on this route towards complexity, and understanding that it's not maybe the phenomena themselves, but it's more like the algorithm, or more the mechanism by which that complexity is achieved, that was the crucial new insight there. Of course, our explorations then led to strong deviations of this classical physical picture. At the one hand, in the search for understanding the nature of space and time and of the universe, and at the other hand, at the other side, we ran into a wall when we started to explain and try to explain things like the atom. And again, there was a radical break necessary with this picture, and we had to develop what is now called quantum mechanics, and that opened the door to the microcosmos. and thereby we got access to this microcosmos. And once we had this, we had a new angle of attack on chemistry. The basic fundamentals of chemistry were laid down from quantum mechanics. And we all know how chemistry, biochemistry, molecular biology, that there is this tremendous development in this direction. And the beauty is, of course, that this is an entirely complementary story to this story, and that's true for the other things too. Now, I have to look at my time here, and I look at half an hour more. Good. I'll not take it all. I was just, this is a grand scheme of things, and in that scheme, you saw already that there are certain turning points in our thinking. So the equations I write in this book and describe, and I'm not going to go through them, of course, I will illustrate a few, are like turning points in our thinking. Turning points in our thinking about nature. In answering these famous questions, what is matter, what is space, what is time, what is our cosmos, where do we belong in this big story? Anyway, there is also some remark I want to make about the nature of these equations, because with the observations and the equations, of course, also the language was developed. And the simplest equations you probably all know, because you have been beaten to death with this in high school. I like the laws of ideal gas, you know. Pressure times volume is proportional to temperature, and there's a universal proportionality constant if you take a certain amount of gas, say. And you can, of course, fill in a number. You can say, if I know the temperature and the volume, then I can calculate that pressure because this number is known. That's fine. But there is also much more qualitative information. You see, this could be summarized in this picture, for example, and also in other pictures, which gives you a global insight in relations, you know. If I keep temperature fixed, I'm on one of these lines, and if I make the volume smaller, sure enough, the pressure has to go up, that kind of language. But that's not all. That was just a simple equation. It's the algebraic type of equations. And in fact, there's much more going on. If you want to try and describe dynamics or processes, you need changes. You want to describe changes. And that was the big contribution, of course, of Newton and also of Leibniz and so forth, to develop this mathematical language of changes and introducing this idea of derivatives. And to make a long story short, because you know all these things, you probably remember from a long time ago, or you use it still. I don't know, but you guys are probably doing all kinds of very fancy stuff. But anyway, the idea of change, you have a function, or you have something that depends on something else. On time, you have a function which depends on time, and you draw the value of that function. Maybe, you know, it's my weight as a person. You see, it went up, it went down, and then it went up steeply again. And you can ask for the change. And of course, then there is this change, you could say, the change in the function compared to the change in the time. And there is a certain steepness associated with it. And that is what we have here. We divide the change in the function, or in the weight, say, as a function of time. Or here, it was the change in the distance by the change in the time, and you get something like the velocity. And you can interpret it just as a slope. It's the theory of slopes. And of course, the first equations were actually doing that. They are dynamical equations. Here is V, the change. And of course, these are the equations that many of you probably have left fields like physics and mathematics at a certain point, because you were beaten to death with that stuff. And that's maybe what you didn't want to do at all. Yet it is remarkable. I mean, it is absolutely remarkable that there was this language of changes and equating them to certain other quantities. And if you now think about many of the modeling going on, whether it's economics, whether it's in ecology, it's all based on this language of changes and written in terms of differential equations. And maybe it's not only time, maybe there are many variables and things can change dependent on many things. And so this is how this beautiful language of differential calculus developed, you see. Here's a function depending on two variables, f is there, and you see its derivatives in one direction or the other can change in different ways. And so you get many derivatives here, and these things can be summarized again in beautiful symbols, like this one here. And so you get to what I call beautiful equations, really very beautiful, like this set is the Maxwell equations, and it says, the Newton equation said, okay, give me the force F is MLA, M times A, then I will calculate all these velocities and these movements. And this is the opposite law. It says, for example, the force could be magnetic, or it could be electric, or it could be gravitational. And here's a set of equations that says more or less the opposite. If you have charges or currents, that means charges moving, then this was telling you how electric, E, and magnetic fields would look like. These equations summarize all of electromagnetic phenomena on the classical level into 4 beautiful equations. And so if you combine them with the Newton equations, then basically you have a closed system of describing motions and of charges, and the charges causing the fields, and the fields acting on the charges again. You would have a kind of a closed system if you leave all the other things out of the discussion. And so that is the basis of classical physics. And you see also the notion became here very important, that there are like fields. Fields are things like the temperature in this room. It's everywhere. There is a certain temperature. And it will change in time, and it will change in the space here. It's near you, it will be warmer than here, and so forth and so forth. So the description and the time evolution of fields is one of the great achievements from the time of the Maxwell equations, which was. And then you can jump ahead and you can say, okay, what is then, for example, I just give a few examples. Here's another magic equation called the Schrödinger equation. It's describing this radical new perspective on the structure of matter that we had in the beginning of the 20th century. You see now, we have all these symbols again. There is a change in time, there's changes in space, and then there is this strange function psi here, which is a field in a certain sense. It depends on space and time again, and this describes the changes. And so there is some field, a matter field actually, because it describes matter. And this is an equation which is the core message of quantum mechanics, and a lot of it is around there, but most of it can be seen as extensions of this fantastic idea that matter are not point particles anymore, but are described by certain fields which have to satisfy such an equation. So, for example, here we saw already it was a field that is much more like a thing that is a wave or something. So the idea was that on a more fundamental level, the particle picture of a point particle had to be replaced in many instances by the idea of a wave. So let me just talk a little about that idea. You see, if we want to characterize a particle, we could say, well, let's take it very simple. It's like a point mass with a certain mass, m, and it has a certain velocity. And then the question was, how can it now ever be related to another concept in classical physics, which is completely distinct? It's a completely different notion. We also know it very well. A wave, yes, a wave. We have all seen waves. They are characterized, for example, by their velocity, but also by their wavelengths. And so how can we now ever relate particles like that to waves? That was the big question. And the answer was, of course, given by quantum mechanics. And let's see. There is a relation here. And that is a deep relation. It's a simple relation. It's algebraic. It says, okay, if you have a mass and a velocity, it's called momentum in the old days, then there is one way you can cook up a length scale here, a wavelength. And in between there is a constant there. That is the famous constant of Planck. That was a new universal constant that we discovered in that time. By looking careful at atomic spectra, we discovered that the laws of Newton and Maxwell wouldn't do. And we had to do some radical change. And you see this constant is extremely small. In our normal units, house, kitchen units, it would be 10 to the minus 34, extremely small number. And that explains, of course, why we couldn't see it, because if there is this small number, 10 to the minus 34, and I have 1 kilo, and I have 1 kilometer a second, or 1 meter a second, then it says that that length scale is 10 to the 34 meters minus. So that is so small, you can never see it. And that's also why it wasn't discovered. But if you think of an electron has a mass 10 minus 30 kilograms. So you get rid of this small number because you divide a small number by small. So this is not so small anymore. And the velocity can be quite high. So then you get into a situation where, say, in the atom, the size of the atom is comparable to the wavelengths of the particle in that atom. And at that moment, things change. Then it's more like you have a bucket of water with waves in it, and you should not study a little ping pong ball or whatever, a billiard ball moving in an atom, but you should think of a wave pattern, and the states of the atom are indeed exactly wave patterns described by that wave equation called the Schrödinger equation. And it brought with it some kind of strange ideas. You see here, I just make a few comments to these kind of equations like they are given in the book. So, for example, here you can see from the Einstein theory, it was known that there was a maximum velocity. I'm not commenting on it today. But here, this should never exceed the velocity c. And you see, c is the velocity of light. So if I put that m times c, then in some sense, I get the smallest possible number here. So this is a kind of the minimal size, because you need the wavelengths to define a wave. And so there is some kind of minimal size of a quantum particle, which is non-zero. And within there is not clear what it is, what it means to talk about the particle. So this led to this famous notion of an uncertainty relation, meaning uncertainty on the most basic level of nature. So let me comment on that relation, and then of course we go on. So here you have an instance of an uncertainty that says, as I said before, there is some kind of minimal size, natural minimal size in quantum mechanics to particles, for example, which have a certain given velocity. And there is the same kind of thing going on with energy here and time. And I would like to illustrate that. So there is this famous statement, it's a deep statement of quantum mechanics, that if the uncertainty in the energy is big, then the uncertainty in time can be small, or vice versa. So if I have a small time uncertainty, so the delta t, you can say here, is very, very small, then this thing has to be large, because the product of the two has to be larger than this fundamental number again. So let me explain that with an analogy in sound. So you could say it's like time and frequency. So let's look at this picture. If I have a sound wave, we can think of a tone, like just, da. It's just one tone. It has a very well-defined wavelength. It's a clear tone. And a well-defined wavelength meant in the previous slide that the momentum or the velocity of that particle is extremely well-defined. So I know exactly, this picture tells you exactly at what speed and what velocity is going. But of course, it is very extended in time. So if I ask you, say, where that wave is, it's very hard. It's not well defined. So to have the proper definition of the velocity, I need a lot of waves. But then it's not localized in time at all. And of course, this is the alternative. That because quantum mechanics doesn't say that you have to be like that. For example, this is also a possible solution to that equation. And what does that mean? It just means it's silent and then it's that. It's just an instant in time, and I get an enormous peak of sound. So it's like clapping my hand. And then you see, here I have a picture where the particle is very well localized, or the sound is localized in time. It's an analogy. But if I ask you, what is the tone here? Yeah, you don't know. It's not a C or an A or whatever. It's in fact a linear combination of all these waves, and all these sounds are in there. So here you could say, you know exactly when it happened, but you don't know anything about the frequency of this wave. And so this is an analogy which somehow explains something important, that you may discover things about nature, that there are certain questions which are, it's not that we are afraid to ask the question, but it seems not quite the right question. You see, I can insist and say, well, I want to know here what the sound exactly is, but is it an A or a C3 or whatever? It is not answerable. It's not encoded here. So it's not a stupid question, but it's not the question you want to answer here. And if you want to go all the way, then you say, okay, well, we have to do this. And then you have another problem. You can't have it all. That is an important idea from quantum theory. Oh. Oh, I'm having it upside down, I think. So let me not go on this too much longer. I want to pass through a few things now. We have learned, and there is something that is, in my eyes, rather astonishing. The fact is that in developing the natural sciences, and in this case specifically physics, of course, because of the equations, because we all know that evolution is an interesting question. What is the equation that belongs to evolution, apart from, say, ecological equations where you just have, that is not what I meant. So there is not a definite single equation, I think, belonging to that part of science. But anyway, here we see something very remarkable, I think. We have all these phenomena, and what happened in the history is that though the phenomena were very diverse, like gravity, like magnetism, like electricity, like optics, like other forces that were discovered, and very slowly, by studying these things, we got theoretical developments which brought these things together. I already showed the Maxwell equations. The Maxwell equations brought together all electric and magnetic phenomena. And actually, since it is also the theory of light, it brought also in optics. So this all was kind of unified in a particular framework of, well, what we saw, electric and magnetic fields coupled to charged matter. And this program went on. So in 1920 we had just discovered these interactions and the nuclear forces which kept the nuclei together, and we had Newton's theory, and then there was Einstein's theory of relativity describing gravity in terms of the space and the time. And so this program went on. I think here we are about just after the war. Quantum theory had been applied to all electromagnetic phenomena. There was a tentative understanding of weak interactions and so forth. And so now this is 1975. You see, relativity and gravity stays aside, but the other interactions are now all integrated into one theoretical framework. In fact, one set of equations which is all based on the same principles. And that is a kind of an interesting development. That's right. Thank you. Yeah, that's a standard model. These two things together form what is now called the standard model. It describes matter on the ultimately microscopic scale on the right side of the picture. This would be the left side of the picture. You could think of this as the large scales, maybe here more and here on the small scales. I will say a few things more about that. But this is, of course, the theory which has been verified now into great detail in all these expensive machines all over the world. But it is certainly a success, because if you see this picture, it is an important historical movement. And then we get into a space of speculation where people are now working on, and people in my institute and so forth are also working on that. I will make a few comments on that later. But there is this idea that maybe this will converge further, and we will have one expression of very few principles which are at the very basis. And you could say the other things that appear are in that sense, should be interpreted as emergent phenomena. I would not like to do all this. You think you are missing out, but that doesn't matter. I mean, maybe if you read in the book, you will learn more. But I try to keep time, and I hope. So this other part, I have discussed briefly something about the microscopic world, how the description of that unified in a few very fundamental new laws that we have written down and that are important. And at the other side, there was this story of Einstein giving us a new understanding of space and time. And of course, his theory of general relativity. I have no time to explain everything in half an hour or whatever. So let's just say that one of the most important and most mind-blowing consequences of that theory was that space and time are dynamical. There is not such a thing as here is space and time and here is physics in space of time. It's not a coordinate system. It's not a pure mathematical thing. It's a physical thing. It responds to the matter in the universe, how the universe looks or what the universe develops to be. And so you could say there are equations for the first time describing the evolution of the universe, or at least the evolution of the universe had to satisfy that set of equations. And more radical, it was unheard of that the universe as a whole would be dynamical, that it would be possible that the universe was not there forever and static. And we all know that Einstein himself had a very hard time. He didn't know, of course, in the beginning that that was a consequence. He had such a hard time accepting these kind of ideas himself. And so in that sense, I think this story of science is one where our beliefs got shaken in the most essential way. It's really something that liberated us from collective myth and prejudices in a very deep way. So to get back to my picture here, well, this is an alternative explanation of the universe. You see there is this committee working on it, and they get, of course, in a big fight, and that is how we explain what we now call the Big Bang, yes? So here it is, and that is nice because I drew you this picture with all these scales. And what is the story? Well, the story is simple now, that if you study this idea of Big Bang, then the matter was all put together very much on top of each other in the beginning of the universe and then expanded, and we are now in this expanding phase. But if you compress everything, things get hot. You add energy in the system. And if you add energy, we all know what happens. If you put energy in this, you burn your hand, then you will certainly burn it. And it will go back to more elementary forms of matter. You will get carbon and maybe some water or things like that, and it will break down further. And if you add more and more energy, these atoms will break down to nuclei and free electrons, and the nuclei will break down, and everything will break down. So if you move to the origin of the universe, which, by the way, is exactly this direction also. Because here you can say, what I see from very far away is there, that has taken a long way to come here. So I don't see what is happening now, I see what happened in the very, very long and early history of the universe. So the origin of the universe is sitting here somewhere. But it also sits here, because at that time, the physics was simple. There was only a few laws and everything looked similar. We only had quarks, and we had photons and these kind of things. So the physics of the larger scales and the physics of the smaller scale talk to each other directly in this, what I would call cosmic event, in this cosmic shortcut. And that's an incredible thing. So that now explains that we have not only this hierarchy of spatial structures, that all matter is in some sense built in the same way, but it also explains why. It is also the temporal sequence of how things came into being. It's exactly that trajectory. First we have only quarks, they bind into little nuclear particles, they bind in nuclei. Then we get neutral atoms, and once the atoms are neutral, then the electromagnetic forces are out, and it's only gravity, so gravity starts pulling things into centers of gravity, and then inside there you get nuclear processes, because everything gets pulled together very strongly, and you get stars igniting, and the origin of structure in the universe as we see it today. And in these big things there may be planetary stellar formation, and they will have accretion disks, and in these disks we can have certain planets, and it goes on. And if we have a nice planet like the Earth, being very mild, you know, in a nice little spot with not large temperature fluctuations, then this complicated chemistry gets going. And if you ask the experts, they probably say, well, life at a certain point will have ignited, and maybe more than once is now the idea. So this is a picture I drew now several times, and you see there's a lot of connections in this picture. So once more, this Big Bang is Big Bang, and in expanding, cooling down, we evolved, and we are at the end point of that. This is another picture of that time. And I find it striking, and that's also why this book has this idea of it's all one story, it's all fitting together. The larger scales talk to the smaller scales. To discover the expansions here and understand this happening, we had to understand light, we had to understand the physics on this level. And as I mentioned already, to get a detailed and quantitative understanding of evolution, it is great that we now also have a way to enter that problem from the molecular side in molecular biology. So where it seemed that all these things, everybody says, oh, science is now so complicated, people cannot talk anymore with you. Well, what happens there and there, it's all specialism and nothing else. Here we see the opposite. If you go deep to the fundamentals, and these equations are the fundamentals, they are the most condensed form of this type of knowledge, then you see it's all fitting together, and there is very little room to think, to see these things as independent. So it's funny that reductionism in that sense has led to a, well, is there something more holistic than this? Than a very unified view of nature and cosmic unity. So I think that was more or less the story. I should finish up. Here is one. I should now finish up, right? So let me. This is something at the end of the book where I draw this cube, which is in the world of ideas, in the space of ideas. You see, I have mentioned a few of these things. I said we started high school. Remember Newtonian mechanics, F is m.a, and the Newtonian law of gravity, mass times mass, inverse square law. And there's one fundamental parameter in there. That's Newton's gravitational constant. And so, unfortunately, we leave our kids in school with this kind of stuff. But we have learned that there were some great breakthroughs. One was associated with relativity, and there is the new fundamental constant, the velocity of light. Because the velocity of light turned out to be an absolute quantity. It's for everybody the same, whether you move such or such. It doesn't matter. It's not time which is absolute, but the velocity of light. And here we went out of that. We added a dimension in our thinking. And here, of course, is, well, maybe I should go back. Here is general relativity, where space and time, you see, get united in one picture, and gravity. So you could say the source of progress has always been conflict. The conflict between this and that was the reason to get there. And then we got this idea of not an idea, we had these observations on atoms, and we had another major new dimension in our thinking about matter and nature. That was related with this Planck constant here. And it is the quantum theory. And then there was a conflict between the old quantum theory and this special relativity, once more. And we got the new theories of matter I discussed, you know, like the unified models. So here is what we know of matter, and it's quantum. And here we have what we know of space and time, described by Einstein. And then you see this picture suggests already that there should be maybe a new type of concept, a new breakthrough, in which matter and space and time become two sides of the same thing. Well, one strong idea in that direction is string theory, but it is a hypothetical theory because it manifests itself at scales which are not accessible to experiment. So this is the equation for string theory. It's one of my favorites because it's nice to work on things that have not been proven. Yes, you know that. So I don't want, oh, no, that is, let me close. This is the map of contents of this book. And so you see it has all these connections we mentioned before in the fundamental constants. So I close with this remark. Yes, these equations are a key to the cosmic code. Think twice, get to know them better. Thank you for listening. Yes?
I just had one that wasn't, I mean, it's something that I thought was a weird coincidence that I ran across, and I wondered if you could enlighten me. I was looking at Schrodinger's, Schwarzschild equation, you know,
Yeah, but you are talking about black holes now. Okay, well, I didn't touch the subject, but please go ahead.
The radius and the mass are proportional.
Yeah.
So, as they get bigger, they're less dense. And then I got curious, you know, what would one the size of the invisible group have as density? And then I looked up an estimate on the web, estimate this,
Total mass of the universe. You looked up what the total mass of the universe was and then checked with the famous equation of Schwarzschild what that size of that horizon would be. And maybe we would fit all in a black hole. Yeah, it's close. Yeah. There are there are many questions actually like that, which are highly, well, puzzling, and coincidences. Many of these numerical coincidences are real coincidences, because the laws of nature do not fit everything. For example, why do we have a calendar? Calendar has, what, 365 days in a year? But the year is the motion around the sun, and the day is rotating about our axis. Now, there is no reason whatsoever that these two numbers have any relation. And if you are careful, you see that it is not true. It's just not true. It's 365. No, not quite. Because, you know, we have once in a 4-year, we take 1 day back, and then once in the, what is it? And then once in a century, we take, it's a fantastic, complicated calculus to just get the rational number, which is the ratio of these two orbital times, divided on each other, and you get some number, and you have to reproduce that in your calendar. So very often there is nothing deep in that. And as far as I mean, it's neat that you observe that. That is indeed remarkable. But there is no answer that I know of which gives more depth to that observation of you. Yes? Yeah. No, please. Okay, this discussion, if you want to discuss ultimate limits, and that's what you are pointing at, is there a mass or something that could really bring us into trouble? Then there are these two simple observations. We just mentioned one of them. I didn't do it here, but there is something about black holes. Let me give two stories and then show you immediately how you get to the heart of all these things. Here's one observation. That's the observation you made. It said lambda is h divided by mass times velocity. So if I go with the mass to enlarge, the wavelength gets short. Big mass, short wavelengths. Larger mass, smaller wavelengths. Okay, that's one picture. And within that wavelength, I cannot say anything about quantum nature of matter, of a particle. Now we have the story of black holes, and you just said it. It said there is a horizon, a Schwarzschild radius. Within, I cannot know anything if I am outside. That radius grows with the mass, linearly. You said it. If I have more mass, that radius grows. So there were two parts of ignorance. One was, the quantum story says, I cannot go inside this quantum wavelengths. And black hole physics says you cannot get inside this horizon. Now, string theory, that clash has exactly to do with that. And it says basically there must be a fundamental mass or a fundamental scale in nature, somewhere. A fundamental quantity which tells you where these two things get the same uncertainty in some sense. You understand? That's what I meant by they become two sides of the same story. Yes, indeed, it can happen and it will happen. And it happens at a very small scale of wavelengths. The wavelengths would be 10 to the minus 35 about, so it's that number again, centimeters or something like that. So it's very, very small. And the idea is if you get to that, why can you understand that? Because if you make, okay, if you want to study the structure of space and time on smaller and smaller scales, you need smaller and smaller wavelengths. You need particles which have larger and larger velocities, because then the wavelengths get small. But large velocity means lots of energy. So you pump more and more energy in this very tiny region to find out what it does. But then Mr. Gravity comes along and says, wait, you put so much mass and energy in this tiny region, it becomes a black hole. Oh yeah, that's too bad. So if you want to study, space and time on the smallest scale, then space and time will cease to exist. Because you get a foam, a cheese of black holes all over the place. So there is this funny idea that you find in physics also the borders of physics. That's where you run into, and that's the moment that we of course not say, okay, now we are done. No, then we start thinking again, say, oh, wait a second, we have to do even more than quantum mechanics and relativity, and we have to get it straightened out there. Well, that is the program of, say, string theory, for example. And so it's, you know, it's briefly announced and so forth. Yes?
You mentioned these, you're supposed to know create a black hole. The ocean question is, if indeed somebody does that, is that like a nuclear bomb where things can get worse and worse, or it's just going to grow and then because of whatever not just make stuff. Basically, if somebody takes a black hole at the end of Earth, or is that just on the radar and nobody will know it?
Yeah, I find a very good question. You know that there is actually speculation a little bit on this. They are building these new accelerators where you get higher and higher energies. Now, let me combine some of these ideas just to get in the neighborhood of your question. You could imagine, that's what string theory says. Well, I said the strings have to be extremely small. But then, of course, in string theory, there are all kinds of schools of thought. There are some people who say, well, in some versions, these distances of these strings can become much larger. And if that is true, that would mean some very strange things. For example, it would not be excluded that in very violent scattering experiments at these accelerators, you would make like prototype of tiny, tiny black holes. Now, I must say that black holes themselves, and this is another famous story out of quantum mechanics, I cannot talk about it, it's not talked about in the book either, it's this famous Hawking. That's why Hawking is so famous. Hawking was famous. Everybody said, okay, things fall in a black hole and nobody can communicate anymore what's happening inside. So they are black, they are dark. Yet, Hawking came along, combining quantum mechanics with the physics of the horizon. And he said, wait a second. In quantum mechanics, you have fluctuations and you can create particles and antiparticles. Imagine you sit right on this horizon and you make this pair, and normally it will re-annihilate immediately. But suppose one of the guys goes into this black hole and the other is stuck there and will not go in the black hole. So he discovered that in spontaneous pair creation, it could happen on the horizon that one particle gets lost and the other gets a boost. It's like jumping off a boat. You know, the boat goes that way, you go that way. So what he discovered was that there are things coming out of black holes, but it is just radiation. It's just temperature radiation. Now, these very small black holes are very unstable. They go immediately with this Hawking radiation. So to say your question, yes, it could be foreign, but it would typically not mean that the whole universe would be sucked up by that black hole made at CERN in 1990. Huh? Great. Yes? Okay, this is a very great question. Sell our stocks, or yeah. You know, I was reading yesterday in the Wall Street Journal. There were two articles that struck me. One was they were trying to sell DVDs on mathematics. So it was called The Joy of Thinking, and you could buy all these beautiful mathematics lectures. And on the other side of the page, there was a short statement by Intel director and Microsoft, Bill Gates, saying that the time of the PC was not over at all. It was just starting, you know. So that is a little bit what I think with your question, you know. What if we know everything? Okay, there are two aspects to answer that question. It could be that knowledge will be complete at the bottom, at a certain point. It's not excluded. There's nothing you can say that would be forbidden. It would be possible to say, well, okay, somewhere in the beginning, it worked that and that. And it's not excluded. I don't say that is necessarily the way it has to go. In fact, there are many other alternatives. But suppose that happens. What does it mean? Does it mean that we understand everything? Do we have a theory of everything? We have a theory of everything exactly in the way I was describing it. There is a bottom to this. And we have the process. I mean, that picture I had in the end was, of course, a beautiful extension of the idea of evolution. Not to the Earth's part or not to life, but all the way down 13.7 billion years to the very origin of things. And matter has slowly learned how to organize itself in that process of cooling. And then every time where there was an opportunity, it would cling together and make structure. And of course, on the Earth, we have this whole chapter of life, and probably somewhere else too, I don't know. But so yes, so now we get back to now we get back to your question, and you know all too well, I mean, if you develop software, this is exactly the same thing. I mean, it grows on you. It goes further and further, generation after generation. It's an emergence business. And it's very hard, if I give you the principal rules of logic 0 1s, that I say, well, once I have told you that, then you understand the Windows operating system. I don't. In fact, I still don't. So this is the problem, that complexity is something that grows, and it is indeed very important to get the algorithms right, to know what drives evolution or emergence or whatever. So that is an interesting puzzle there. But if we have a theory of everything, quotes, unquotes, it is certainly a theory of everything, because there will be not other forces involved. There will be, like every computer, it just works by the laws of quantum mechanics and all these things. There is no way around that. But we found many new inventive ways to use those rules and make new things. And so the knowledge is incomplete while the bottom of things is complete. Maybe.
Yeah, this is really intriguing, but kind of like my physical world, you know, that I can touch and see. And I'm thinking about your process flow of wonder,
Yeah.
know, and I'm thinking about the create, the make, the look. And what practical consequences do you see of a lot of the work that you do in college or at this point?
Yes. Of course, it's good, because you pull the discussion back from the loop to the other side of it. Also there, just like what Bill Gates was saying yesterday, we are only at the beginning, I think, of a lot of things. For example, quantum mechanics, we learn to manipulate matter more and more on a fundamental scale. Really manipulate it, play with it, pick an atom and put it somewhere else. So the rules of quantum mechanics, which we understood already, and which we also knew explain a lot of the properties of matter in all kinds of forms, and even complicated biological molecules, we now start playing with it. And often, if you can do the experimental things very well, that means also you are at a point that you can manipulate things. Think of genetic engineering. Often nature itself gives you the instruments. You first have to discover them, and then they say, here's the toolkit. You know, genetic engineering, there are enzymes. They do cut and paste, and you can do it all. And you get it at the moment you do the discovery, because nature has to do it one way or another itself. So yes, that equipment is all there. And that's what you all the time discover. Now, I'm just connecting up to your question in the sense of computers, and then of course there's the speculative thing of marrying quantum mechanics to computing, for example. It's called quantum computers. And to tell you the truth, that's the workshop I'm now running, actually, at Santa Barbara with new friends from the lab here. And so that's a wild idea. That is rather long term. But if it happens, and nature does these things, but if we get a handle on that stuff, it will be kind of a great revolution in computation, I think. And it will have many new applications where you now would not go very easy. And it doesn't mean it's the end of this. It means just there is another way to do computation and another new type of physical basis for computation. And I don't know, but if you, informatics, of course, is now a classic informatics. And quantum theory introduces a new type of informatics also. So there's a whole theoretical school of making algorithms, or having an informatics theory based on quantum principles. And so this is a new area that is a long range, but you could think that is at a certain point it becomes truth. It reminds me a little bit of what I was saying at the beginning of my talk. I said, well, when I brought the people of Philips in, and I said, look, here, what they are doing. They are all working on screens, and they have a mouse and all that. And the guy said, well, this is just child play, it's all bullshit. We have to work and go on with our machines. And they were in this corner and they didn't understand that there were all kinds of people in Stanford at that time working on software, just on software. They said, well, if everybody has a computer on his desk, which was an impossible thought, then we better make sure that everybody can use it, or whatever they did. It's great. They were ahead. And so I think, yeah, if we do something like quantum computing, which is completely crazy from a, down-to-earth today's perspective, it may be in 25 years that we talk completely differently about it. So that's an example. Yeah.
I'm seeing more people are around string theory.
Oh, okay. Oh, sorry. No. 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 I would say the string theory attempt is one which really goes much more in the direction of a cultural. It's very important. Like discovering general relativity, well, I have to make a side comment to that actually. But anyway, was something that we discovered that the universe was expanding. The idea of a Big Bang, the whole idea of a dynamic universe is of a tremendous cultural impact. It has changed our view of all kinds of things. So that's the application of it in people's minds. At the same time, this theory was so far away from daily practice, we thought. But if you now think of the global positioning system, this little machine in your car and whatever, that actually uses general relativity in a critical way, because it's always satellites. Clocks run slower and faster depending on where they are in the gravitational field. These are all effects of general relativity, special relativity and general relativity. And you have to do very careful calculations to get indeed your position on a centimeter or a meter accurate. That is all applied general relativity. And so there's this old famous thing that, who was saying that? I think it was Faraday. And they said, well, what is the use of electromagnetic theory? Maxwell's equations. And he said, well, I don't know, but one day they will tax it. So, I don't know whether string theory will ever be taxed, but I would be happy to get some of that money, though. Well, it goes on. Yeah, no, you should. One more question. Okay, maybe you.
Lots of science really closer. As myself not religious, do you think it's still true now with the thing we have believed? Do you really, I mean, when you look at your beliefs, what's your religious belief?
Oh, okay.
So when you look at
Yeah, that is a big discussion. In this country it has been very fierce and very intense. Of course there has been this big debate on, but now, I mean, I give a personal perspective on these matters, yes? On religion and science, and what is the relation. There is a comfortable way to deal with it, and many scientists do it. They say, look, there is matter and there is spirit, and that's the way it is. That's there, that's there. No problem. What is the problem? The problem has to do, there is, of course, we are all talking about a single reality in some sense. Okay, so this is where there is tension. There is a real tension there. Because, for example, I don't want to, I mean, I respect everybody's things, and I have also a nuanced view on it, I think. But one of the discussions you get, and I have also those discussions, is the idea of intervention. Intervention means somehow interacting. So if you say, okay, let's separate the things. That's where, you know, religious actions take place, and this is where scientific actions take place. Then there's this delicate question. Does your God intervene in this world or not? Does he or does he not? No, he does, because he manifests himself in all kinds of ways. And then you get a slightly uneasy discussion on the fact that how is this action realized and what is it? And of course then we have this debate where people say, okay, well, the Big Bang, you don't understand it, so that's where he is working. But suppose that this theory does tell you more or less that there was a story of evolution from 30.7 billion years ago, which in some sense is rather autonomous, and these equations more or less describe what's going on. That is a kind of a strange situation, that we could have had all kinds of interventions which would have shown up as completely not clear how this would have happened. And of course so you can always speculate on these things, but then if you talk to scientists, they will always ask you, well, what do you really mean? Do you mean this or that? And you get always a little bit into trouble. So I think the debate on intelligent design, I think in the country has also been more or less finished, or no, not finished. Okay. I think no, I think among the scientists you have always just people who, go to church and all that. Why not? Because it is a social institution which has all kinds of functions, and of course it is there. So it's a reality. But I think that many of my colleagues, if you ask them, did God create the world or did the world create God? Is it a product of evolution or the other way around? Well, then I think that many of the people in the harder sciences will have that view that maybe, it is a product of an evolution, and it had all kinds of evolutionary functions, and it is obvious that it has that, and that's why it has been reinvented all over the place, just like the eye or like something else. It is a solution to a certain problem of collectivity, and, well, that's a view on religion you can have and maintain. And I think many people in fields where I live think that way. But there are very outspoken scientists of great class who have the opposite view. So be careful. Yes.
Thank you very much.
Well, it was a pleasure.